So the other thing that we look at from stars is stars give a characteristic signature for hydrogen. So these black lines represent the signature for hydrogen from stars, right? So whenever we see these spectral lines, there's a certain pattern at certain wavelengths between 400, 500, 600, 700 micrometers. That would be the spectral lines for hydrogen. A different chemical element like silicon or copper, they would have different spectral lines, right? So we'd see a different signature. But for hydrogen, this is what we see. So what this is showing here to emphasize this redshift is that a star like ours, or maybe even Alpha Centauri, which is about 4 light years away, a nearby star will see those characteristic spectral signatures for hydrogen. But then when we look at like the Andromeda galaxy or in a galaxy that's nearby, we see those same patterns, but note that they're a little bit shifted toward the red end of the spectrum here. And then when we see another galaxy that's farther away, we see there's a more pronounced shift toward the red end of the spectrum. Then when we look at the most distant galaxies in the universe, we see that there's a very strong red shift toward the red end of the spectrum. So this is what redshift means, is that when we look out into the cosmos, the light we see from stars, this hydrogen, indicates that the galaxies, the stars, are moving away from us, right? So that emphasizes the expanding universe. And so the analogy is this idea of the Doppler effect, right? So your book has a little figure here on as a train. So the train approaches you. If you were standing by a train, you would hear a high pitch, right? Because the waves are compressed, and you would see shorter wavelengths. So that would mean that the object is moving toward you. As the train pulls away from the station, you would hear a lower pitch, which means that the wavelengths are longer, right? So that's telling you that the object is moving away from you. So that's the analogy with stars. So because we see the longer wavelengths, we know that these stars, these galaxies, are moving away. So that's the criteria for the redshift and the expanding universe. And so physicists try to explain this in a more simple term. When we bake bread, the yeast allows the bread to inflate, and so you can think of these raisins as galaxies, right? So before the expansion, the galaxies were maybe 1 centimeter away from each other, maybe half centimeter for this one. But as the bread is baked and the yeast causes the inflation, the rising of the bread, we see that the galaxies are now farther away, right? So each one is farther from each other. Kind of to summarize, another thing that when to think about this cosmic microwave background radiation, in 1965, Arno Penzias and Robert Wilson from Bell Laboratories discovered this radiation above absolute zero, right? So it was everywhere, pervasive in the universe. And that's what this map, this W map, is showing. It was really done in 2012 by people at Johns Hopkins. And it really shows this temperature anomaly of the universe. So wherever we look, we see that there is this energy out there. And so again, that's evidence for the Big Bang, that it did occur, the afterglow of the Big Bang. Now, the other thing that they determined during this WMAP study was that a big chunk of the universe is about 73% dark energy. And dark energy is sort of like an anti-gravity energy. And this anti-gravity energy will really cause the universe to keep expanding, right? So because some people propose that maybe if there was a Big Bang, will there ever be a big crunch because gravity will bring everything back? But because we have so much dark energy, anti-gravity, that this universe is going to keep expanding. So anyways, we form the universe, right? We get the Big Bang going. And so what happened in the first 3 minutes, right? So physicists, we talk to physicists, they'll say that there was this immense inflation event. So suddenly the universe went from no space to having an enormous amount of space, right? I think they say it went from 0 to about 53 million kilometers, and it dropped by about 1 billion degrees centigrade in those first 3 minutes, right? So again, you get in the first trillionth of a second, you get this immense expansion, inflation of the universe, In that first second, you develop the four basic forces. So the four basic forces that we start seeing: gravity, electromagnetism, right? So electricity and magnetism. And then we see the forces that work within the atoms, like the nuclear force. So the strong nuclear force keeps protons together in the nucleus. Because one thing we'll learn about protons are positive. So how can all these positive charges be held together? Because remember, positive charges or like charges will repel each other, right? So there's a nuclear force that's holding those in the nucleus. And the weak nuclear force is radioactivity, right? So we'll talk about the different forms of radioactivity. So after 3 seconds, the universe cools enough to form protons. We start seeing, so remember, one proton would be the chemical element of hydrogen, right? So we start seeing hydrogen, and so the first element that formed was hydrogen. Maybe a little bit of helium, maybe some lithium, but most of the universe is hydrogen. And even today, most of the universe is still hydrogen. And that's the fuel that stars use for nuclear fusion. And then again, after about 3 minutes, we get this expansion to about 53 million kilometers. It cools a little bit, and then we see Big Bang nucleosynthesis. So this means that instead of just forming hydrogen, we're probably going to form helium. We should probably say that we're forming helium and lithium. So two other chemical elements that were formed during the Big Bang. Which means elements like carbon, nitrogen, oxygen, silicon, which is important for rocks, they didn't form at the Big Bang. So they're going to form inside of stars by nuclear fusion. So now we have hydrogen, a little bit of helium, some lithium, but now we need to make heavier elements like carbon, nitrogen, oxygen, silicon. So where does this occur? So there's a process that's called nuclear fusion, and this occurs inside of stars, and stars are about the only thing massive enough to bind lighter elements, two nuclei from two different atoms, to bind them together to make heavier atoms. Remember, the way we define atoms is by their atomic number, and the atomic number are the protons in the nucleus, right? So for example, hydrogen has 1 proton, helium has 2 protons, lithium has 3 protons, oxygen would have 8 protons, carbon has 6 protons. So what are these stars? So stars are incandescent spheres of hydrogen, so they're using hydrogen as their fuel, and they do nuclear fusion. So here is a Hubble telescope image of the Eagle Nebula, which is in the constellation Serpens, right? So here's Serpens here in the night sky. And this is actually a gas nebula where hydrogen is coming together, and really stars are being born here, right? And then once the stars reach massive enough or large enough size, that gravitational energy of bringing this gas together turns into thermal energy, and eventually it becomes massive enough to start doing nuclear fusion. So here, nuclear fusion, here we're going to take deuterium, which is a heavy isotope of hydrogen. So remember, there's 1 proton. In this case, it has 1 neutron, so we call that deuterium. Some hydrogen is called tritium, where again, it's still hydrogen because it has 1 proton, but here it has 2 neutrons. So if we take deuterium and tritium, both isotopes or heavy isotopes of hydrogen, and fuse them together, we'll make helium, but we have this extra mass, and that's the energy. So that's the binding energy. So this binding energy takes place inside of stars. So this extra mass left over is converted to kinetic energy, right? And it really follows Einstein's formula. Energy equals mass. That's key, right? Energy equals mass. So in this case, the mass of this extra mass that doesn't go into the helium converts to energy, and that's the solar radiation we feel. So remember, we're going to multiply that mass and the speed of light squared, right? And the speed of light is already a ginormous number, 3 times 10 to the 8 meters per second. So we're going to square that. So that little change in mass leads to a tremendous amount of energy, right? So again, this takes place inside of stars. So we're binding lighter elements to make heavier elements. And stars are even the big massive blue stars, the ones that actually explode into supernova, you can only bind up to atomic number 26. So one way we look at chemical elements is, for example, if we look at the chemical symbol for iron, by convention we put the atomic number as a subscript before the chemical element. So this is telling me that iron has 26 protons. But then up here we're going to put the atomic mass, or the isotope. So you can think of this as the isotope. And the isotope is going to be the protons plus the neutrons. And one thing that we'll talk about later on when we do minerals is that neutrons have a positive and a negative charge. So that's why they neutralize each other. So remember, down here, these are only the protons down here, positive charge, but these are protons and neutrons, right? So that's why this number is larger, because you're adding the neutrons and the protons. So that's also the atomic mass, we call it, right? The atomic mass. Whereas down here, that's the atomic number. Another example, if we look at carbon, carbon has 6 protons, and most carbon is carbon 12, although in this class we'll look at carbon 14, which is the one that's radioactive. And there's also carbon 13 we look at because, especially when we start looking at early life, we look at the composition of graphite, which is composed of carbon, between carbon 12 and 13. And it kind of gives us clues as to about when photosynthesis or life started on planet Earth. But anyhow, that's a little bit on some chemical symbols there. If we keep going here, we'll see that so if we're making iron inside of stars, then how do we get atoms heavier than iron, like copper, silver, gold, uranium, right? That's one of the really larger chemical elements. And so that has to happen in a supernova event. So during a supernova event, basically we're putting energy into the atom, right? So really, supernova events, 2 functions. One, for the supernova event, we're going to form atoms heavier than iron. And the second thing that we're going to see is that we're going to shatter heavy atoms into space. And these heavy atoms, these are going to be the seeds for a solar system. In fact, we're going to start small. We're going to introduce a word here called planetesimal. So that's what happens. Stars go, it's really the giant stars, the ones that are blue hot. There's red hot, there's white hot, and then there's blue hot. And blue are the really large stars, vigorously using up their hydrogen fuel and then exploding in these supernova events and forming heavy atom elements that go into space. And so our star is maybe a 3rd or 4th generation stars, but several stars have already exhausted their supply of hydrogen. So they collapse and begin to generate heat, driving element production. So our sun is maybe a 3rd, 4th, or maybe even a 5th generation star that has greater proportion of heavier elements than previous stars. We are made out of that material. We are stardust. So basically the calcium, the phosphorus, the sulfur, the nitrogen, the carbon in your body at one point formed inside of a star. Well, let's stop here for now.